All right. Sorry about that, everyone. So as you can see, we have a very complex setup now involving two slideshows. But so to introduce myself, I'm Shane Howley. I work with Mainframe, and one of the things that we're interested in is building cool things on top of PSS. And now, this is actually what I only look like when our designer edits my slides, but normally I look like this on GitHub.
Can you talk to the mic, please?
Sure. Do you want me to use the handheld, or I'll just stand closer.
Oh, yeah, there we go.
So, what do we already know about PSS at the network level? We know that PSS can be used to send encrypted data payloads to an address or partial address in the swarm overlay network. We know that the overlay network is routed by nodes sending encrypted dev P2P payloads to their Kademlia peers. And we know that the underlay network is routed by nodes sending TCP payloads across the internet. So to sum up some useful properties that we already have, TCP gives us reliable payload delivery, but only between pairs of connected peers. TCP also gives us some information about connection liveness. So if we're connected to someone else, we know if this connection is alive or dead. But again, this only works between connected peers. Dev P2P allows us to send pretty large payloads, significantly larger than TCP allows. And PSS gives us encryption and integrity to our payloads. But maybe, as I have alluded to by pointing out that some of these properties are only held between connected peers, there are some limitations to using PSS. For example, when a message is sent into the network, you can wait for a response, but was it received? Is anyone there? You might just have to pray. There's also no guarantee of message ordering. So even though TCP ensures that messages are sent in order between any two connected peers, this guarantee doesn't extend across multiple hops. For example, when redundant routes are used to deliver a message, some routes may deliver a message quicker than others. These two aspects can cause problems for large payloads also, as the sender could have transmitted large amounts of data before knowing whether the receiver was even ready to receive it. These issues can be solved already by dealing with ordering, acknowledgements, and retransmissions up at the application layer. But this is quite a burden to leave at the feet of front-end developers building on top of PSS. So another way we can solve these issues is to just add a layer on top of PSS to make it behave similarly to something developers are already familiar with, sockets. And given the Swarm project's fondness for acronyms, I'm calling this PSS socket PST. And just to summarize the... But now we have a T. Okay, maybe we can talk about it more after. So just to summarize the goals that I'm setting out to achieve with this protocol, we want to set up connections between nodes to indicate a willingness and readiness to receive data. We want it to be reliable, meaning that we want to guarantee that all the data we sent is received at the other side. We want to send arbitrarily sized data payloads and have them reconstituted on the receiver side before they're processed. And we want data to be ordered so that segments are received and processed in the same order that they're sent. So just some of the inspiration I got while researching this. When considering how reliability can be built on top of an unreliable protocol, a good place to start is looking at TCP. At a high level, PSS shares some similarities with UDP, so any existing protocols that attempt to build reliability on top of that or IP directly are also interesting. And I was also interested in data framing to allow large payloads to span multiple PSS messages. So I also took inspiration from WebSockets. So this is what the segment format looks like for PST messages. The most important detail we have here is are the control flags, which are in the first byte, and these are used to control the connection state. So there is synchronize, which is used during handshaking to agree on the connection parameters. Acknowledge, used to inform the peer that segments have been received in sequence. Extended acknowledge, used to inform the peer about out-of-sequence segments received. reset used to tear down the connection, and null, which is an empty segment used to poll if the connection is still open. And when used to transmit data, the overhead per PSS message of the PST header is 8 bytes. So we're going to look at some protocol examples now. And in these, there's already an implicit assumption that Alice and Bob have already exchanged keys, addresses, and topics, and these are being used at the PSS layer. So PST uses a 3-way handshake similar to TCP to agree the connection parameters. And one of the peers needs to begin in the listening state. Now Alice can attempt to open a connection by sending a SYN segment containing an initial sequence number and some connection parameters. Bob acts this segment, sending his own initial sequence number and connection parameters. And then finally, Alice acts Bob's segment, and the connection is opened. One of the aims for the reliability logic is to minimize unnecessary retransmissions by acknowledging out-of-order segments. In this example, Alice is sending a payload spanning multiple segments. So she sends segment 101, and Bob acts it. She sends segment 102, but it never arrives. Then she sends some more segments, 103 and 104. They are received by Bob. Now, Bob detects that some of these segments are out of sequence, so he sends an extended ACK. So to do this, he acknowledges the last in-sequence segment, which was 101, and EACs 103 and 104. Now Alice has the knowledge that segment 102 didn't arrive and can retransmit it. And then finally, Bob acts 104 as the last in-order segment he received. Under a normal operation, though, the peers may not be as eager to ACK or retransmit as in this example. For example, segment 102 may just have been delayed and received after 104 here, meaning a retransmission would not be required. During handshaking, some of the parameters that are agreed are timeouts for this and ACK frequency. When a connection is idle, periodically a null segment is sent to test the connection liveness. So if Alice sends a null, Bob should respond with an ACK for the most recent in-sequence data segment. But if there's no response, Alice assumes the connection has failed, so we'll send a reset segment, mark the connection closed, and inform the application layer of this happening. One of the parameters that can be configured is the maximum PST message size. So I believe currently dev P2P allows messages up to 16 megabytes. But sending a payload this large in a single PSS message could be wasteful if the recipient is not prepared or drops out mid-transmission. I haven't investigated this quite yet, but I wanted to test if aligning the max size such that a PSS message could be encapsulated inside a single TCP packet and check whether that has any difference in performance efficiency versus just like sending really large PSS payloads. As you see here, the way in which payloads are framed is pretty simple. The size is encoded at the beginning of the frame using LEB128, which is a base 128 encoding for variable-sized integers. So for example, up to a 127-byte payload will use a 1-byte size field. Up to 16 kilobytes would use a 2-byte size field, and so on. And once the recipient reaches the end of the frame, that is, when they receive that number of bytes across segments, the message is handed up to the application layer. So some of the applications that I think could be useful for are games, collaborative editing, real-time messaging, or really anything that requires, any P2P application that requires some kind of shared state and syncing that state, so maybe like a CRDT. Yeah.
So it's string-based, not datagram-based anymore?
It's kind of like message-based, so I consider UDP like datagram-based, where it's just sending like individual like payloads of data, and you're handling them as they come. And then TCP, which is stream-based, where you're just getting bytes, and eventually you need to decide where the cutoff is. But with this, it's message-based. So you on the sender side, you send like fully framed messages, and they're received as fully framed messages in the application layer. But I mean, at the end of the day, everything's bytes. But like as a developer, this is the way you'd work with it, right? Yeah. The PSS layer is like the closest analog would be datagrams. So the current status of the project is that the protocol design is basically complete, and this is kind of what I've talked about here. The next step is to make a prototype of this and have it integrated with PSS so we can play around and see what kind of things we can build with it. Another thing I'd like to do is use the network simulation framework to like simulate different network conditions and see how the protocol performs there. And also produce a formal specification so that there can be like competing or alternate implementations that can coexist. Some potential improvements I'm already thinking about could be added. I mean, at the moment, I'm just trying to keep it like relatively simple, but you know, I'm still thinking of ways we can kind of make it better. One thing is adding more subprotocols. So PSS is already kind of a subprotocol of Swarm, and Lewis's talk earlier was about building subprotocols on top of PSS, and you know, subprotocols everywhere. It'll be great. Yeah, so WebSockets actually do this when they're like setting up the connection. So I think it could be something that you can do during handshaking to say like, I want to talk this protocol, and then the handshaking can decide whether the connection is successful or not based on this. Another thing which I also noticed in WebSockets is allowing unknown length payloads. So when I spoke about the frame, I said always the start of the frame told you the size of the payload. But there could also be applications where you don't know the size of the payload ahead of time. But I couldn't really think of a great use case, so I kind of didn't want to make it overly complex. And maybe there's other great ideas that like the community has, and I'd be interested in talking to people about that. Where you will eventually be able to get updates is probably on our company GitHub, Mainframe HQ. There's no repo there yet, so this is why I have not told you that. But if you keep watching there, eventually one will appear. And that's it. Thank you.